evening, ladies and gentlemen. Welcome to Lecture 8 of Topic 1 of Unit 4, Lenz's Law and Transformers. This video is going to be covering the main ideas of Chapters 8.3 and 8.4 of Book 2. Please complete this reading before class, and shout out to Mr. Brewer, who apparently is watching these videos before most of you students do, so you want to pick up your study habits there, guys. Here are your learning intentions and success criteria. Please have a read, pause the video, and attempt to complete the KS table down there on the bottom right. Okay, so having a look here, we can see that we're going to try to explain this thing called Lenz's Law in terms of conservation of energy, and you do need to be able to explain it, and you have to apply it to determine direction of the EMF. Now, we saw EMF in our previous video. Now we're going to figure out how to do the directional parts of it. So, our success criteria, you need to explain it in relation to conservation of energy, determine direction when magnetic flux changes, and then explain how a transformer works. Knowledge, well, what is Lenz's law? What is a transformer? A bit hard to explain either of these things, we don't know what these are. And then in terms of skills, well, how do you apply this law? So, in our previous lesson, we saw that a changing magnetic flux near a circuit will induce a current. Okay? But current requires a direction, so how do we determine the direction of the current? And the answer to that is conservation of energy, going back to year 8 and some of our stuff with thermodynamics at the start of this year. So here are two components for an induction setup. We have a moving magnet and we have a resultant electrical current. So we can see the magnet moving here, and as the magnet moves we can see the currents being generated, some sort of amperage here. Now when we move the magnet, before we get into that, there are two types of energy here. There's kinetic energy in the magnet and there's electrical energy in the circuit. So we have two types of energy and there must be some connection between the two. Now when we move that magnet, we transfer energy from us. Okay? Now this could be replaced by things like waterfalls, rivers, steam from burning fossil fuels or nuclear radiation. And so the energy is conserved there. My kinetic energy, I have to do some work to give it kinetic energy, or the river slows down a bit, or some of the heat is used up, essentially used up but transformed into this rotation of some device in order to create this induction effect. But a magnet doesn't get used up, at least not from this. So does that mean the electrical energy is free? Because here, if we have some kinetic energy and we don't have this coil, we just have kinetic energy. But if I move the magnet near it, the kinetic energy hasn't changed, yet suddenly there's electrical energy. That's free energy, isn't it? But you can't get free energy. That violates the law of energy conservation. Now remember our first law, energy cannot be created or destroyed, only conserved from one form to another. So there has to be something else here. Okay? You can't get something for nothing. Lenz's law is the solution for this conundrum. Okay? Lenz's law states that the magnetic field direction of an induced current opposes the magnetic field that created it. Okay? So here's a bit more formal definition. The magnetic field of an induced electrical current acts to oppose the direction of the field that created it. To put it really simply, if you move a north pole to a solenoid, you get a north pole appearing, pushing back against it. If you move your north pole away from a solenoid, you get a south pole trying to pull you back. Okay? Because we know about the direction of magnetic poles and solenoids, then we can use our right-hand rule. So remember our right-hand curl rule. Okay? If my thumb is the direction of the field, we can use this to work out the direction of the current around the solenoid. You can work it out using that. And the way I like to think of it is like a magnetic inertia. A field is created to keep the magnetic flux the same. Okay, this is a really important point because there are some examples we're going to look at that don't actually involve coils. So, since the magnetic field then opposes the magnet, okay, it's pushing back against the magnet, the movement of the magnet slows down. It loses some kinetic energy. And that loss of kinetic energy becomes the electrical energy. So that first law of thermodynamics, the law of conservation of energy, is still true. Okay? The field pushes back against the magnet, and so because of that, we end up losing a bit of kinetic energy, but we gain some electrical energy. That means, remember, if your magnet is still, there's no field being created there. This unfortunately is a bit too weak to feel easily, but you've all seen that video in class of dropping the cannonball down the length of tube, and the induced current slows the cannonball that has the magnet fixed through the middle of it down, so that a field above it pulls up the magnet and a field below pushes up against the magnet, and that way that's Lenz's law in action. So let's have a look at a couple of examples of this. Now, for some reason, actually, here's a little really basic animation I'll try to make. So here is as our magnet moves in, we get a north pole being created here. So red for north, blue for south. Then, when we start to move the magnet away, a south pole gets made because it's trying to pull it back. It doesn't want it to go away. Doesn't want it to come any closer. Doesn't want it to pull away. Doesn't come any closer. It's like a bad-tempered ex-girlfriend or ex-boyfriend, okay? You're trying to get away, they try to pull you back. You try to get close, they try to push you away. Okay, it doesn't want you to change anything. It's like inertia. Okay, like law of inertia we learnt in year 10 or last year for everybody, for year 10 or year 11. So, let's have a look at an example here. And this one looks a little bit more complicated because this is a fairly common way of teaching about Lenz's law or applying Lenz's law. Now, this is a bit of a different situation. We have here a set of rails going through a galvanometer, which is just a fancy ammeter, so it's going to measure current. Okay, so we have a galvanometer around there, and we have a rod here, but the rod is going to move. Okay. Oh, sorry, this one it's about changing the field strength. Here we just have a rod against it. Just consider it a circuit. Okay. We're not putting any ammeters, we're not putting any solenoids on it. The solenoid example is pretty straightforward. This is slightly different, okay? Now, we have here the magnetic field strength in figure 4 changes from a value of 0.2 Tesla to 0 in a time of 5 milliseconds there, okay? Now, we're going to do the math part first, and that's going to be no different from what we did in our last video, and then we'll look at the direction in a second, and the direction we need to apply Lenz's law. So let me just turn on that light. Oh, my cat has decided to sit. Put that over there. And we can see okay. Yep. So, we have here a square, and we'll put the magnetic field. Magnetic field is going this way into the page, and the square is 0.2 by 0.2 meters. We are told that B initial equals, where was it, 0.20 Tesla, and B final equals 0. And the time it takes is equal to 5 milliseconds. 5 times 10 to the negative 3 seconds. Always convert, makes it so much quicker. Don't even worry about writing it down with the prefixes there. Let's see, anything else from a question? Oh, N. There's just one loop, so N will equal 1. Okay, now our EMF formula, remember, EMF equals negative N change of BA cosine theta divided by the change in time. Now, we can see here that the area is flat and the field is going directly into it. So the perpendicular vector, so this is my area vector, they are parallel. So the angle theta equals 0 degrees. Now, our B is changing here, so it's going to be negative N A cosine theta times the change in B divided by the change in time. Okay. In this case, our change in B is going to be equal to negative 0.20 because it's 0, take away the whole thing. So negative delta B equals 0, take 0.2 equals negative 0.2 Tesla. Yeah, that's Tesla. So, let's substitute. Negative 1 times our area. Well, our area is a square, so 0.2 times 0.2 times the cosine of 0 times our delta, negative 0.2, all divided by our time, which was 5 milliseconds. 5 times 10 to the negative 3. Now we substitute all that in, and we get a voltage of 1.6 volts. Okay, so there's the math. The math is a little bit complicated because you've got to worry about what you change, but we can see it's mostly going to be just finding the stuff off the question, substitute. Now what about the direction though? Remember, Lenz's law says the goal is the flux doesn't change. That's the goal. And we want to do stuff in order to keep the flux the same. Now the magnetic field here has got weaker. So what's going to happen to the magnetic field that's being created? Well, the magnetic field, think about it for a second, the magnetic field is getting weaker, then it's going to create a field that is trying to make it stronger. Okay, and so it will generate, therefore, induced field into page. Okay, if this is getting smaller and weaker, it'll try to keep it the same. It'll try to keep pushing it down. Okay? Now, that means, in terms of the current, now it has been labelled here D, A, B, C. You know, it's a square. Let's think of it like a coil. A square is just a weird looking coil. So if the field is going into the page, then that means, okay, by our right hand rule, let me just double check my video. There we go. Okay, it is coiling clockwise. Therefore, so our I will be this way. Alright. As soon as the field stops moving, the induced current would go away because the EMF is no longer changing. But as it is changing, as it gets weaker, it would go that way. If we take a guess and think, well, if the field is getting stronger, well, the induced current would act the opposite way to try to make it weaker. And so then, because the induced current would act that way, then our coil would end up going the other way. Okay, so as long as we understand Lenz's law that the flux doesn't change, okay, if the field gets weaker, got to do that. So field changing an area constant is pretty straightforward. Angle changing is a bit weird, but I don't think it's really something that you would be doing all that easily. So it's more likely going to be either area changing or the magnetic field changing, or you're going to have two solenoids like we'll see with transformers in a second. Okay, so let's have a look at the other example. Okay, so this one's on the next page, down on page, what is that, 223. Inducing an EMF by moving the rod. Okay, so here now, because we're moving the rod, we're going to end up changing the area. Okay, which means, well, we've seen that if we change the area of a magnetic field going through an area, we're going to have a change of flux, and so we would have an induced EMF, and that is indeed what we see happening. Alright, so let's get that jotted down. Okay, copying down the diagram here. So we initially have an area like this, which is 0.2 by 0.2. Put a few crosses in it, and it becomes 0.2, and we add an extra 0.05, so that would be 0.25. Okay, so I'm going to add an extra cross in it just to show that there is a bit more going through it. We still have our sound B field. Our B is, where is it? Remaining constant its initial value, which in the previous question was equal to 0.2 Tesla. 0.20 Tesla. It's just one loop, so n equals 1. And the change of time... Oh, okay, so we're saying here now we've got a velocity, so we will deal with that in a second. Right, velocity. Okay, velocity equals 5 centimeters. Interesting. It actually has skipped the per second here on the descriptor. I'll double check to see if that error has been fixed up. Alright, so 5 centimeters per second. Well, this has gone from 0.2 meters to 0.25 meters. So, well, that's 5 centimeters, isn't it? So that means the time that it takes to do it must be equal to 1. Now, remember, velocity equaling displacement over time. We've got velocity, we've got the displacement 5 centimeters. We can work out the time from that. As a bit of advice, while linear motion was not part of your coursework this year, this formula is part of the Year 10 coursework. So it is expected that you can recognize basic movement stuff. Okay, just be aware of that. There is a derived formula in the study tip on page 223. Remember, that won't be mentioned in your what's what I'm looking for in your formula booklet, but it might be a useful thing. It's not really worthwhile remembering because this is going to be a very unique, rare situation. Remember, when in doubt and you're just I can't figure out what the time is going to be, just guess a time. Pick one. Okay, make the math a bit easier for yourself. Say, well, it's going to have an area change of this much. I just don't know how fast it's happening because I just can't figure it out. I'm going to assume t equals 1. You'd lose 1 mark, okay, for getting the time wrong. But the carry error through would be fine. Just write a little assumption next to it. Can't work out the time. Going to assume 1. And then the rest of it, just go with it. Okay, so let's look at our area. Our area initial equals 0.2 times 0.2. And our area final equals 0.2 times 0.25. Okay. Now, what's that going to be equal to? They've actually drawn a little bit of an image there to show, well, that's the change in the area, that little extra bit here, which you could do, because that little bit there would just be equal to 0.05 times 0.20, but there's nothing stopping you from doing this to work it out. Let's see, so 0.2 times 0.2 would be 0.04, and as my calculator, 0.2 times 0.25, 0.2 times 0.25 is 0.05. Okay, so delta A just equals 0.05, take 0.04 equals 0.01, which if you did that, that's what you would get. Okay, meter squared. Now we have everything we need. We have our B, we have our N, we have our time, we have our A, and the theta, remember, will just equal 0 because we're still dealing with perpendicular things. So, EMF equals negative N times B times the cosine of theta times our change in area divided by our time, negative 1 times 0.2 times the cosine of theta, which is just going to be equal to 1, times our change in area, which is 0.01, all divided by 1 second, and we would get an answer of 2 times 10 to the negative 3 volts. Did I make a mistake on the previous page? No, I just didn't do the substitution, that's fine. Alright, oops, sorry, that's negative. Can't forget the negative. Though he has just written a magnitude of it, the negative will matter in a second. So, let's think about what's happened here. The area has got larger, so the change in flux is positive. Okay, we have our B times cos times A. There's our flux. The change of flux, okay, is going to be a positive thing in this case. Most of the time, the previous question, the change of flux was negative. That's why we had a negative at the top multiplied by a negative, and we end up with a positive. But here we have a positive, so we're increasing the flux. That means the field is going to oppose it to reduce the flux. Okay, so let's just show this. B A cos theta is positive. Remember, BA cos theta equals pi. That's our change. Okay, therefore, Lenz's law means we reduce the field. Because it can't reduce the area, the only thing it can reduce is the field. Okay? Now, the field is going into the page, so we need something the opposite direction, which means it'll come, where's my hand? Come up towards you. Okay? Yeah, just double checking. And so then we end up with our current going the other way. So I goes that way. Right? So that's all you need to do. If the EMF ends up having a positive change here, then it's going to be acting against it. Okay. If the EMF goes the other way, if it ends up having a negative part here, then we end up having an increase in order to make sure that the field doesn't go away. That's why when you pull out a power cord too quickly, while the power is still running through it, it sparks, because it's trying to induce a current to keep that spark there, to keep that electricity flowing, because it doesn't want you to change anything. There's some great videos on this of magnets falling through aluminium tubes and copper tubes, where you can see that things get very slow because there is a very large induction of force. Okay, so that's Lenz's law. Now, transformers, because transformers are an application of these things. We've seen solenoids have magnetic fields, and we've seen if you change a magnetic field, you get an induction effect. Okay? And if you change the magnetic field, okay, or the magnetic flux near a solenoid, you can make a current get induced inside that solenoid. If we combine these two principles together, we get a transformer. Now, the transformers I've shown you in class, remember, have a big air gap in the middle of it. But if we replace that air gap with something magnetically soft like iron, which focuses the magnetic field lines, we saw that in the last video and when we did our sketching of field lines, the changing field of one coil, okay, will induce a current in another foil, because it will condense down the iron core and be ferried right through the middle of it. And it kind of looks like this. Okay? So here we have a coil, and we have a DC power supply with a switch. When we turn this on, we get a magnetic field. We can see it's running out the north here, coming in through the south. And as we change that field, instead of going, just leaving here and coming back through, will go all the way through, okay, the iron core here, before coming back around. And so there will be a magnetic field running through here. Okay. Now remember, because we're going to induce a current in it, if this is north on this side, it will create a north pole on this side to oppose it. Okay. That's our Lenz's law. Keep that in mind. Now, on a DC circuit like this, you'll only get this effect when you turn the switch on or off. If you think about when I have moved the magnet inside the solenoid and we see the little magnetic lever sort of meter thing on the other solenoid move, remember, if I'm not moving the magnet, it doesn't move. Okay, you need to have a changing flux, you need to have a changing field to get a current. When I turn the switch on, there's a changing field, there's a changing flux, so we end up with a current over here. But once it's on, the field isn't changing, it's still constant. When I switch it off, then we get another field. Okay, so 90% of the questions for these will involve AC current, alternating current. And so the direction won't matter a huge amount except in a single instant type thing, in a picture that kind of looks like this. When it looks like this, we're just dealing with the single instant of there being current flow. Okay? If the question says specifically it's DC, and it says, with a current running, you can just turn around and say, nah, there's no induction, so you don't have to do anything. It only would matter if the DC is being turned on or being turned off. So if the question's not specifically saying that, you can be cheeky and kind of dodge the answer a little bit. Now, if both sides of the transformer, okay, this side and this side, have the same number of coils, then the induced circuit will have the same voltage and the same AC frequency. But if we have a change of coils, then we will end up with a change of voltage. Okay. Alright, now, with our transformer, if we assume there's no energy loss, then we get these equations. Now, there's a derivation in the textbook. It's not necessary for you to prove, but do keep in mind, I think it's important that you keep in mind that these assume that there is no loss of energy, that it is all perfect. We have voltage, and the ratio of the voltage is the same as the ratio of the number of coils. That's what our N stands here for. And we can also use this to work out the current. Okay? P for primary, S for secondary. Okay? P is for the one that is where the electricity is flowing, and S is for the one where the electricity is being created. If you end up flowing electricity the other way, it doesn't matter which you say is the primary, which you say is the secondary. It really doesn't matter. We could replace P and S with 1 and 2, but the language of this is very much about primary and secondary coils, because there's normally we're wanting it to go one particular way. The electricity in your house, for example, hits the power pole near your home, comes down from 400-ish volts down to 240 to get pumped into your wall, reaches your computer, gets pumped to get spun down again, gets stepped down again, and becomes what your computer needs, so that it is not going to blow your computer up, which is kind of important. There's a little bit of terminology to do with the ratio here. If this ratio, if NP is bigger than NS, so the ratio is a number greater than 1, then this is called a step up. If the ratio is less than 1, so that NP is less than NS, then it's called a step down transformer. That terminology doesn't appear in the syllabus, but it might be worthwhile just keeping in mind in case that sort of language is used, and it's not too complicated. So let's have a look at an example. This is the example from chapter 8.4. Transformer purchased from an electronics store is labelled 240 volt AC input, 50 volt AC output. It has 400 turns of wire on its primary. Two things we're going to do: calculate the number of turns and tell me, is this a step up or a step down? Alright, so if we have a look at the question, and I'm going to do a couple of things here. We'll also assume some original current, and we'll work out how much current is going to go through this thing, just so that we can see both formulas in action. We have our voltage for our primary, our incoming voltage, 240 volts. That's the AC input, and our voltage on our secondary is the output, 50 volts. And we are told we has a number on the primary of 400, and we want to know what's the number on the secondary. The formula, let's just sub it in: Vp over Vs equals Np over Ns. Some text you will see write it actually as Vp over Np equals Vs over Ns. Oops, little n. And it means the same thing, it's just been rearranged. It really doesn't matter which you remember. I did this one in high school, and that's still the way I went to write it, and I had to double check what the syllabus has it written as before changing to this on my notes. So it doesn't matter, because you can see that they're just rearranged for each other. Substitute them in. 240 over 50 equals 400 over something, NS. Let's rearrange that. We're going to get NS equals 400 times 50 over 240. So NS will equal 83 turns to two significant figures. Remember, you can't really have half a term. I mean, I guess you kind of can, but just round it to a whole number, especially depending on what sort of information has been given to you here, because there's a two sig figs there. So 83 turns. So that's part A, pretty straightforward. Part B was, is this a step up or a step down? So NS, okay, is less than NP. So 400 divided by 83, that's greater than 1. That means it is a step down transformer. You can also look at the voltage, because the ratio of this will be the same as the ratio to this. So we don't need this information to work out step down. 240 down to 50, that's why it's called a step down. Okay, the voltage is going down, therefore it's a step down. So we can write it a couple of ways: VP greater VS, or NP greater NS, therefore step down. Now I'm going to do an optional extra here. This is not on the in the book. Let's say that the original current on the primary is let's say 0.5 amps. Okay, and we want to know, well, what's the current on the secondary going to be? Okay, so now we're going to have the other formula. So IP VP equals IS VS. IP I made up as 0.5 amps. Voltage primary 240 equals IS times 50. Well, 0.5 times 240 is 120. Divided by 50 equals IS. And so we can see IS here equals, what's that? 2 and 2/5, so 2.4. 2.4 amps. Quite a bit of amperage there. So this actually tells us something important though. When we reduce the voltage, the current has to go up. Okay? And if we think about it, well, we learnt about our power equation, P equals IV. If this thing gets smaller, that has to go up. The power hasn't gone anywhere. Okay, so you can see here, this is connecting all the way back to the circuitry stuff we did back in Unit 3 months ago. These things all connect to each other. It's really important to keep that in mind, that all these things are true. It's not just one thing at a time, and nothing else can apply to it. All right. So, in this video we have done the following: how to explain Lenz's law in terms of conservation of energy, how to apply Lenz's law to determine the direction of an induced current, and we've calculated voltage change in transformers and explained how they worked. Okay, the explaining part is the actual descriptor out of the syllabus, but I have a feeling that voltage change might be something that could appear in relation to that, so it's worthwhile knowing the formulas, especially since the formulas are in the formula booklet. So it's kind of like they're saying, yeah, you'll probably have to do it, but we're not going to say directly that you have to do it, so we just want to cover that just in case. For your entrance slip to class, please complete questions 1 to 6 in chapter, I did not update that, whoops, 1 to 6 in chapter 8.3, just ignore this, and 1 to 5 in chapter 8.4. Copy your answers into the 4.1.8 space on eLearn. Don't do this. This is from the last video. I forgot to update that. So questions 1 to 6 in chapter 8.3, 1 to 5 in chapter 8.4. Alright. Have a great night, guys. See you next time.